Today I'll talk about some of the work that's going on in our group over the past 5 to 10 years to address the system size as well as accuracy limitations in electronic structure calculations. This is joint work with Sambit Das, who is one of the core members of this long program. Bikash Karungo, who is a research scientist at University of Michigan, and Fani Motamari, who is at the Indian Institute of Science. So I have a few introductory slides for those who are not from the electronic structure community. The starting point of all electronic structure calculations is the Schrodinger equation. And if you're interested in the ground state properties, it is the time-independent Schrodinger equation given by h psi is equal to E psi. So h over here is the Hamiltonian, and I've written the non-relativistic description of the Hamiltonian. So we have the kinetic energy of electrons, kinetic energy of nuclei, the electrostatic interaction between electrons at little ri and nuclei at capital Ra, the electrostatic interactions between electrons and the electrostatic interactions between the nuclei. So now if we look at the wave function depends on the positions and spins of the n electrons as well as the positions of the m nuclei. And it is common in quantum mechanical calculations to do what is called as the Born-Oppenheimer approximation, where you treat the nuclei classically. So for fixed positions of the nuclei, you're then solving this many-body Schrodinger equation, where you're trying to compute for this wave function psi. And if you look at this wave function psi, this lives in a 3n-dimensional space. So that's an exponential complexity, which is hard to overcome. And this is where chemists have made many approximations on the representation of this particular psi, and that gives rise to a series of theories, like be it Hartree-Fock, multi-configuration equations, and so on. But there was this dramatically important statement that was proposed in 1964 and 65 by Kohn and Sham, which said that as long as you're interested in the ground state properties, then that is solely a functional of the electron density. Now, the electron density, which is the probability density of finding an electron at any spatial point, it's a field in 3 dimensions. So you've reduced the problem from solving for a variable in a 3n-dimensional space to solving for a variable in a 3-dimensional space. And that's not hard to see. So the energy of the system is given by psi h psi, which is greater than the ground state energy. Or on the flip side, you can say that the ground state energy can be computed by minimizing over all admissible wave function psi of psi h psi. Now, this operator, which is the interaction between the electrons and the nuclei, is a single electron operator. So that reduces to being integral of the electron density times the external potential. Now, these first 2 terms are still dependent on the explicit n-body wave function. But you can write this minimization into 2 minimizations. One, a minimization over all electron density rho, and another a minimization over all wave functions giving a particular electron density rho. And you can, if you look at the problem, which is inside this round brackets, that gives us a functional of rho. And one of the important aspects is that this f of rho is completely independent of what system we are talking about, because the information of the system is in this external potential. So this is a universal functional, but the holy grail is that we don't know what the functional form is or what its representation is. So Kohn and Sham did a clever trick where they took this functional and split it into the following 3 terms. So the first term is the kinetic energy of non-interacting electrons. This is the electrostatic interaction, classical electrostatic interaction given the electron density. We know what the functional form of this is. And all the remaining terms are lumped into this so-called exchange correlation functional, which now is the unknown. Now, this Ts of rho can be indirectly computed by looking at the Euler-Lagrange equations of this particular variational problem. And if you take the Euler-Lagrange equations, you end up with the Kohn-Sham eigenvalue problem, which is, so this is the Kohn-Sham Hamiltonian. We have the Laplace operator and the effective Kohn-Sham potential, which is the mean field in which all the electrons are moving in. Psi i's and epsilon i's are the single electron orbitals and the energy levels. Now, this effective potential depends on the external potential, the Hartree potential, which is your classical electrostatic potential, and the exchange correlation potential, which is the functional derivative of the exchange correlation energy. So the V effective depends on the electron density, but the electron density is computed in terms of the single electron states. So this has to be solved in a self-consistent manner. And once you do that, you can compute the ground state energy in terms of the single electron wave functions as well as the electron density. And once you have that, like, you can compute a range of properties. But now if we look at the computational complexity of this calculation, that typically scales as order n cube, unless you do something special like what David was mentioning in the previous talk, where there's certain classes of systems or with assumptions of locality, you can reduce that computational complexity to being order n. So this is a citation map to citations to the seminal work of Walter Kohn and co-workers. And you can see that DFT is used in many, many fields. And in fact, there was a survey article in 2014 in Nature which looked at all the highest cited papers across all the fields. And 12 of the 100 most cited papers were related to DFT, and 2 in the top 10 as well. So given the vast importance of DFT to many, many fields, there have been over 100 DFT codes that have been developed over the past 40 years or so. And there's also an exponential increase in the usage of the DFT codes. And as you can see, some of the most widely used codes are plane wave based, and the reason being that they provide systematic convergence. So you can converge to arbitrary accuracy. But at the same time, if we look at what the relationship of the DFT codes is to high performance computing these days, I think this cartoon by Anubhav Jain nicely sums it up. Still, many of the calculations, as David was mentioning, are in this high throughput material science regime where you have lots and lots of calculations that people do in the regime of few hundred atoms, but you're not able to still effectively use the high performance computing platforms out there to solve challenging problems. And as David mentioned, one of the issue is that most of these codes developed out there are cubic scaling, which have difficulty in terms of dealing with large systems to begin with. But also one of the key issues is lack of parallel scalability, which is that you try to throw these codes on many more cores, they don't scale very well. And that is partly because many of the Fourier or plane wave based codes, you have to take Fourier transforms very often, and that does not scale very well on parallel computing architectures. But as David mentioned, again, there are many good examples of why we need to get to larger scale calculations. This could be trying to understand properties of nanoparticles, biological systems, or defects in materials where you will have to go to many thousands of atoms. And I'll present some examples related to defects in materials. Okay, so in our group, we've been working for the past 10 years or so in developing systematically convergent algorithms as well as a computational framework to do large-scale DFT calculations. And we've been focusing on the finite element basis. And my presumption is that everyone in this audience knows the details of finite element basis. So they offer systematic convergence. You can either adaptively refine your element size, or you can bump up your polynomial order to get to arbitrary accuracy. One of the strengths is spatial adaptivity, and it can also treat complex geometries and boundary conditions. And one of the significant advantages is the potential for excellent parallel scalability. And these advantages were known to people for a very long time. And in fact, the earliest works which explored finite element basis for density functional theory calculations actually date back to the late 1980s. But what they found was that to get to chemical accuracy, which is roughly 0.1 millihartry per atom in terms of energy and 0.1 millihartry per Bohr in terms of the forces, they needed almost 1 million basis functions per atom. And that was basically the point where finite elements was explored but never became a competing basis for the other basis sets. But one of the things that people did not look at more carefully was when all these studies were being done, they were using lower order finite elements, either linear finite element or quadratic finite elements. So they had not explored the higher order finite elements in a more systematic manner. In 2013, we started looking at these things, and just to impress upon the need for higher order finite elements to be competitive computationally compared to other basis set, let me take these two examples. One is a copper nanoparticle, another is a periodic system, molybdenum with a vacancy, modest or very small system sizes, 50 atoms or so. So here I'm showing how many finite element degrees of freedom one would need to get to chemical accuracy as a function of the polynomial order. And you can see that for both these systems, once you go to fourth order, there's almost 1,000-fold decrease in your required basis functions. And that 1,000-fold decrease actually also translates into a 1,000-fold decrease in the CPU time as well. And that was one of the things which I believe people missed for a long time, that when we are doing electronic structure calculations which require very high levels of accuracy in terms of relative errors, the need to go to higher order finite elements is very important. Okay, so the other advantage is the spatial adaptivity of the finite element basis itself. So one can come up with error estimates, like where you bound the ground state energy in terms of the finite element mesh size. You don't need to have this finite element mesh size to be uniform, but in fact, this can be a function of R, and you can then solve an optimality problem to figure out what will be the optimal distribution of the finite element mesh size for a given problem to get to a given accuracy for a fixed number of elements. And you get adaptive meshes like this. So this one is for the copper nanoparticle. So if you use adaptivity, you can end up getting another factor 5 to 10 boost in terms of the required degrees of freedom. So the other downside of a finite element basis is that it's a non-orthogonal basis. So which means that when we discretize the problem, we end up with a generalized eigenvalue problem. Now, one can go and transform this generalized eigenvalue problem into a standard eigenvalue problem using the Loudon orthonormalization, but that requires the evaluation of m to the power half and taking its inverse, which when you have a large basis can be computationally very expensive. So here is where we use spectral finite elements. The difference between a conventional finite element and a spectral finite element is that the nodes in a given element for a conventional finite element are equispaced, whereas in the spectral finite element, they're placed at the roots of the Shabisha polynomials or the derivative of the Legendre polynomials. So one advantage of the spectral finite elements is that it gives you better conditioning of the basis, but also another key advantage is that if you use the spectral finite elements in conjunction with the reduced order integration rule, such as Gauss-Lobot or Legendre quadrature rule, that makes your mass matrix to be diagonal or the overlap matrix to be diagonal. But in terms of error, the quadrature error that you're making over here is exactly the same order as that of the discretization error. So we use full Gauss quadrature for the Hamiltonian matrix, but we use this reduced order quadrature for the overlap matrix. So with that, the transformation to a standard eigenvalue problem now becomes trivial. And once we have the standard eigenvalue problem, we use what is called as the Shabisha acceleration technique to compute the eigenstates of interest. This was proposed by Yusuf Saad, Jim Chelokowski, and co-workers in 2016, and then we adapted this in 2013 for the finite element basis and removed some of the inefficiencies that were originally there. So the main idea behind the Shabisha acceleration technique is the following. So because we're interested in the ground state properties, what we're interested in are the eigenstates at the lowest end of the spectrum. So let's say that this is the spectrum of the Hamiltonian. We're interested in this lower end of the spectrum, which I'm calling the wanted spectrum. We really don't care about this unwanted spectrum. And the main idea is that you scale and shift this particular Hamiltonian such that the unwanted spectrum comes between -1 to 1, and the wanted spectrum comes to the left of -1. And once we have that, we can construct a Shabisha polynomial filter and then hit it on a bunch of random vectors. And what the polynomial filter would do is that because the Shabisha polynomials are bounded in -1 to 1, but grow very rapidly outside of -1 and 1, what you end up getting is a space which is rich in the wanted spectrum. And once you have this particular space, then the idea is to project your original problem into this filtered space and solve much smaller diagonalization problem for your DFT. And one of the key advantages of Shabisha filtering is also that this can be done recursively, so which can be reduced to essentially a matrix-matrix multiplication. Okay? So if we look at the algorithm that we use, so we do the Shabisha filtering, then we orthonormalize this Shabisha filtered basis to get an orthonormalized set of vectors from the filtered basis. And then we then project the problem into this filtered basis and then diagonalize it and then rotate back to the original space to get the wave functions in the finite element basis. From that, compute the electron density and then repeat the self-consistent field iteration if the output electron density is different from the input electron density. Now, if we look at the computationally most intensive parts of the calculation, it would be this Shabisha filtering step that scales as order mn, where m is the number of basis functions and n is the number of eigenstates that we are evaluating. That's the Shabisha filtering. The orthonormalization scales as order mn square, and the Rayleigh-Ritz scales also as order mn square. So I'll now briefly discuss some of the HPC aspects that we brought to bear to accelerate these three steps as well as reduce communication volume in these three steps so that we get better parallel scalability. So when it comes to Shabisha filtering, the main kernel that we are trying to use over here is a h times x, where h is the discrete Hamiltonian in the finite element basis, size m cross m. Now this is a sparse matrix because of the locality of the finite element basis. And x is this dense matrix m cross n. And typical, or not typical, but some of the largest calculations that we have done, m is roughly of the order of 500 million, and n is of the order of around 70 to 80,000. So we are talking about close to 40 trillion entries that you will have to store in this particular matrix over here. So it can get challenging. So you have to be very careful as to how you do this matrix-matrix multiplication. So as is the case in any finite element code, we do a domain decomposition, where each of the color represents a particular partition in the decomposition. And in terms of the memory layout of this wave functions, we store all the n wave function values corresponding to a given finite element degree of freedom in a contiguous manner. And what we do when we have to compute this kernel is not try to do this in a naive way using sparse dense matrix multiplications, but we recast this particular evaluation into matrix-matrix multiplications at the finite element cell level and then assemble things back. So to do that, we have to extract out, we extract out a block of wave functions because we don't want to extract out all the wave functions because that's going to increase the memory footprint. We get a block of wave functions, and from the global entries, we actually evaluate what the wave function values are going to be locally at the finite element level. And then once we have that, doing this h times x is going to be massively parallel. And then you can use strided batch xgems to do this. And now you get element level values for this matrix Y. And eventually there are two assembly operations that you have to do. One is an assembly operation for the finite element nodes that are shared across the element boundaries. And we use atomic add operations to avoid race conditions to be doing that. And then finally, you also have to assemble across your partition boundaries, which is essentially where the boundary communication between the different partitions show up. But here, one thing about finite element basis is that the number of nodes on the partition boundaries is far fewer compared to the number of nodes inside of a domain itself. So we do this particular communication across the partition boundaries in single precision, and that allows us to cut the communication volume by a factor 2 and then boost the parallel scalability. And also, because we are doing this h times x for blocks of x, as the compute for one block is happening, the communication for the previous block can happen. So you can even overlap compute and communications. So this is the, yeah.
Assembly is gather, right? Is this?
Yes. Yeah. So, so this is the performance, or this is somewhat of an older result. So here, like I'm showing the performance of just this h times x for a system with about 1,000 electrons, and this is on 2 nodes of Summit, and then you can go up to over 25% throughput. This was with a polynomial order of degree 5, but more recent calculations that we're doing with polynomial orders of degree 8, we can get the throughput on Summit to be above 50%, and on Frontier to be above 40%. And you also get like a very good CPU-GPU speedup, almost 20x on the 2 nodes of Summit, if you use all the CPUs on the 2 nodes versus using the GPUs on Summit. Now the next aspect is the orthogonalization step, and we use the Cholesky-Gram-Schmidt to do the orthogonalization. And in this particular aspect also, we can use a mixed precision idea. So as the SCF iteration is progressing, because we use the wave functions from the previous SCF iteration, the Hamiltonian has changed a little bit, but the wave functions still are a reasonable representation, a reasonably good guess for the new Hamiltonian in the next iteration. So as a consequence, what happens is the overlap matrix is diagonally dominant. So we compute the diagonal entries in double precision, and then we compute the off-diagonal elements in single precision. We do the Cholesky decomposition in double precision, and then we compute back like what the orthonormal basis sets are. Even over here, like we can, because even this matrix is going to be diagonally dominant, like we can use a mixed precision even over here. So again, we use the blocked approach to overlap compute and communication. So we compute a block of S matrix, and while the compute of this is happening, a previous block's communication can happen. So we take advantage of this asynchronous compute and communication idea to boost the performance. So this is a benchmark on about 60,000 electrons on around 1,300 Summit nodes. So here I'm showing what would be the performance for the overlap matrix computation as well as the orthonormalization step in double precision and in mixed precision. So there is a substantial increase in the performance. And once we overlap compute and communication, we can pretty much hide either the compute behind the communication or communication behind compute. Question?
This is 2 electrons per atom, right?
No, this one is 10 electrons per atom. So this is a hard pseudopotential because 2 electrons per atom was not doing a good job for the kind of problems that I'm going to discuss in a little bit. Okay, so the final step is the Israeli-Ritz step. You project the Hamiltonian into the Shabisha filtered, orthonormalized Shabisha filtered space, you diagonalize it, and you do the subspace rotation. Again, over here, you can leverage an aspect of mixed precision. So if we look at these wave functions, many of the wave functions which are in the core are going to be fully occupied. And there are only going to be some wave functions which are going to be fractionally occupied. And we care about the eigenvalues only of the fractionally occupied states. Because as long as we have a subspace spanning the occupied states, we can compute the electron densities corresponding to the fully occupied states. So once we have the split, if we have this 2x2 block matrix for the Hamiltonian, we can compute all these 3 blocks in single precision and only the tail block in double precision, which is where we want to compute our eigenvalues. And doing that, again, in subspace rotation also, we can do the diagonal part, like in double precision, and the off-diagonal parts in the single precision. So again, even over here, we use the blocked approach, and using mixed precision and overlap, you can get a substantial boost in the performance. Yeah.
So have you ever tried to characterize if there is any error that's introduced by that?
Exactly. So three benchmark systems, modest system sizes, a non-periodic copper nanoparticle, and these 2 are periodic systems with getting to about 10,000 electrons. So this is the error between the mixed precision calculation and the double precision calculation. In terms of the error in energy, negligible. In terms of the maximum force error, also 2 orders of magnitude lesser than what people typically care about. And one of the other things is the number of SCF iterations that you get between the double precision and mixed precision, which is stable, which means that the robustness of the calculation is not getting affected. However, we also try to reduce further the precision and then go to half precision, and then things don't work. So it's only up to single precision that we are able to use this trick.
So these are unrelaxed structures? They're just a bulk lattice with one atom removed, or you're doing a structural relaxation?
No, these specific benchmarks are the unrelaxed structures. But we regularly now do relaxation with mixed precision, and then we don't see any issues. We are doing realistic calculations.
But if the structures are relaxed, so the maximum force error probably just irrelevant, right? Because that is the equilibrium.
No, this one is the maximum force error between the double precision and the mixed precision.
But like during a relaxation?
So this is for a given snapshot of the positions of atoms.
Atoms are in equilibrium, right?
No. So these are not relaxed. So for instance, in this particular nanoparticle, you could have actually forces which are fairly high, order 10 to the power minus 1 Hartree per Bohr. Okay. So this is a comparison between DFT Fe and Quantum Espresso. So as a benchmark, we took this molybdenum system. It's a periodic calculation, which is where the plane waves are the most efficient. We're using ONCV pseudopotentials, which David mentioned in the previous talk. So this is with a mono vacancy, and we considered supercell sizes of increasing system sizes, going all the way up to 2,000 atoms. And these were run on Cori KNL. And this is how many node hours would you need for a single SCF iteration. And both these calculations were done at the same accuracy, which is 0.1 millihartree per atom for DFT Fe and 0.1 millihartree per Bohr in terms of the max force coming from discretizations for both these codes. And what we see is that as the system size grows, you can get a substantial speed up or reduction in the number of computational cycles you need for the calculation. And if we look at a non-periodic system, and this is the copper nanoparticle, the crossover between DFT Fe and Quantum Espresso happens at a much smaller system size. And as you keep increasing the system size, there's a dramatic difference in terms of the computational time between these codes.
Do you use periodic boundary conditions?
So for DFT Fe, we don't, because we can apply non-periodic boundary conditions. But for Quantum Espresso, we applied periodic boundary conditions, but on the cell size, like where you were getting to these particular accuracies. So the domain sizes were different for DFT Fe and Quantum Espresso in this case.
Vikram?
Yeah.
Sorry, have you got any insight as to why the Quantum Espresso scaling is so bad?
So
this is worse than NQ.
Yes, that's because they become completely communication bound. Once you start trying to push the system sizes larger, and they're not compute bound anymore.
So it's all the FFTs and the...
Yes, it's all communication bound, yeah. Yeah. This was KNL, yes.
For KNL benchmarks, I think, at least I would guess, also have the problem of the intractable memory hierarchies of KNL. And that could actually play in disfavor of Quantum Espresso here if they run into another level of the memory. That's not correct.
Yes. So we were not going beyond the recommended 32 cores per node for running these calculations.
The actual memory hierarchy in the KNL chip was a real problem.
Yeah, it's possible. Yeah. So we don't have the benchmarks on a different machine, but I'll show you at least some of the minimum wall times on DFT Fe so that people who are doing Quantum Espresso calculations, they can get a sense of where DFT Fe can stand compared to Quantum Espresso. So I have more benchmarks coming up. Okay, so this is strong scaling in terms of time to solution for a pyramidal dislocation. This has about 2,000 atoms, around 20,000 electrons. Good scaling up to many tens of thousands of MPI tasks. as well as good scaling on many thousands of GPUs as well. So for a user of a DFT code, I think this is the slide probably which would be the most meaningful. So here we're showing for the same molybdenum benchmark system, what is the minimum wall time per SCF iteration that you can get if you scale Quantum Espresso and DFT Fe both on the Cori machine, the kernel architecture, as well as DFT Fe on Summit using GPUs. And we scaled both the codes such that the parallel efficiency does not drop below 40%. So we see almost a 10x difference in terms of the minimum wall time on the same machine, Cori, and then another 10x in terms of minimum wall time on Summit. So for systems of the order of around 30,000 electrons or so, we can get an SCF wall time down to about close to 10 seconds. So,
excuse me.
Yeah.
What kind of system size? Like how many GPUs, how many CPUs?
Okay, so this I'll have to go back. So Summit, would that be like 300 nodes of Summit? We can check back and let you know. Yeah. I think it's roughly, at least for this system, I think it's a few hundred nodes of Summit.
Few hundred nodes.
Of Summit.
Even for the GPUs?
Yes.
Okay.
So DFT Fe, it's an open source code. You can download it over there. These are the two manuscripts which actually describe all the details of what went into this code. Some of the key aspects are it can treat periodic, non-periodic, semi-periodic boundary conditions. It can do both pseudopotential and all-electron calculations. All-electron calculations is non-relativistic at this point. The functionals, like we can handle density-based LDA, GGA with van der Waals corrections. And we're also working towards incorporating hybrid functionals. It's in a separate branch, so we've already benchmarked these things. We can do ground state calculations, full relaxation, Ab-initio MD. We've tested system sizes up to 100,000 electrons pseudopotential and 10,000 electrons all-electron calculations. And we got about 38% efficiency on Summit and 64 petaflops. These are some of the older numbers. We're trying to get newer numbers now, both on Summit and Frontier. But that's where the code stands. And I want to talk about maybe a couple of applications, to demonstrate what are the kinds of problems we're tackling with DFT Fe. So one of the problems that we are trying to understand is pathways of improving ductility in magnesium. Magnesium is the lightest structural alloy that we know, but people don't use this very much in automotive industry because it's very hard to form materials out of magnesium because it's a very brittle material. So the ductility in magnesium is partly governed by the dislocation activity. And so if we have a metal like aluminum, which is face-centered cubic structure, you have many slip planes on which dislocations can form, nucleate, and then glide. But when it comes to magnesium, which is a hexagonal close-packed structure, these dislocations can form on the basal plane and glide on the basal plane very easily. Energetically, they're not favorable to nucleate and then glide on these prismatic planes. But experiments have observed that these dislocations can actually form and glide on the pyramidal planes. Or rather, they've observed dislocations on the pyramidal planes. But what calculations show is that if you have a dislocation on one of the pyramidal planes, it dissociates onto the basal planes and then gets locked up because it's no longer a glacial dislocation. But one of the hypotheses that people have been exploring in the past 5 to 10 years is, can you actually alloy magnesium to increase the activity, the dislocation activity on this pyramidal planes? So if you have a pyramidal dislocation on pyramidal 2 plane, can you make it jump onto pyramidal 1 and make this cross slip and then such that you can get better ductility in the materials? So for this model, one of the things that was completely unknown was what is the energy difference between a pyramidal 1 and pyramidal 2 dislocation in magnesium? And people tried to use VASP. They went up to, I think, 1,000 atoms because you have to relax these things very tightly. This energy difference is a very small energy difference. But they couldn't even get the sign right. So the sign was telling something different than what experimentalists were observing. They couldn't use interatomic potentials because depending on what interatomic potential you use, either you were getting the sign different or qualitatively, like, there was a very large spread. So this is unpublished work, but we were able to actually systematically converge this energy difference with respect to the system size. We went up to 3,000 atoms, 30,000 electrons in a 2.5D calculation times 12K points. So we are essentially computing around close to 400,000 eigenstates in these calculations. So we are now able to compute what this energy difference between the dislocation of the pyramidal 1 and pyramidal 2 planes is, comes out to be around 16 MeV per nanometer. And one of the things that we saw was actually that this energy is actually not a constant, but actually sensitive to the macroscopic deformation that comes at the core of the dislocation. And Sambit has also conducted painstaking extensive calculations of how this energy changes when you add solute atoms at the core of the dislocation. And with that, he has also developed a model which is explaining quite a number of experimental data points very well. So he's going to talk about that, I believe, in workshop 2. So we're also looking at solute segregation energies because these are important in terms of understanding how grain boundaries can rotate and slide so that you can control and get non-basal structure, non-basal textures in magnesium polycrystalline materials. Again, these calculations involve many thousands of atoms now, which are possible with systematic convergence and verifiable accuracy with DFT Fe. A few other examples, we computed the electronic structure of a DNA molecule having 100 base pairs and trying to understand the electron structure underpinnings of electron transport in such biological molecules. And this is a work which is joint work with Julia Gali, where we were trying to compute the spin Hamiltonian parameters, where you actually needed all electron accuracy to be able to compute these spin Hamiltonian parameters accurately, because the code provides systematic convergence for all electron calculations. This was possible. Okay, so now shifting gears, we've also been trying to think about, can we improve the accuracy of DFT calculations without sacrificing the efficiency of the DFT calculations, right? So and when I mean accuracy over here, I'm saying accuracy of the exchange correlation functional itself. So that's the physics that's going into the calculation. So the broad framework that we have in mind is the following. So let's say that we're able to do many-body quantum calculations. I mean, these are possible only on small system sizes. If we are looking at CI calculations, this is only possible maybe on tens of electrons. If we go up to quantum Monte Carlo, these things would be possible up to, Paul, correct me if I'm wrong, but about 1,000 electrons. So once we have the ground state energies and densities for the various systems, if we are able to solve the inverse DFT problem, that is computing what should be the exchange correlation potential field, which gives us back the same density, then that is the true exact exchange correlation potential for that density in that system. If the ground state density is ab-initio correlated, right? I mean, so these potentials will only be as good as the theory that you use, that you get the densities from. But if you're using the best theory out there, then these are exact up to that particular theory. Then there's a potential of using these exchange correlation potential fields and the electron densities to maybe improve the exchange correlation descriptions that are out there. But one of the main bottleneck in realizing this framework was the solution to this inverse DFT problem itself. And this was the formulation is very straightforward on paper, but it's a very numerically challenging problem. It's an inverse problem, so it's expected to be ill-posed. But many attempts over the past 25 years in solving this problem, what they saw was that when they tried to invert or compute some kind of multiplicative potential based on either iterative approaches or direct approaches, they saw spurious solutions in the exchange correlation potential. Or if you try to regularize it, you were getting solutions which were highly dependent on the choice of your regularization. And from my perspective, the two main issues were that, firstly, the densities that we were getting were from an incomplete basis. They were mostly computed in a Gaussian basis because many body calculations can be efficient using these Gaussian basis sets. But you have wrong asymptotics then, because so this is the electron density of a hydrogen molecule along the bond length, and one needs to have a cusp at the nucleus for the density. But if you use a Gaussian basis, you do not have a cusp, you have a zero slope, and that is incorrect. As well as the decay of the electron density, if you use a Gaussian basis as Gaussian, as opposed to it has to actually be exponential. And the second aspect is that the inversion itself was in an incomplete basis. Now, the same basis sets which were going to describe the density well need not describe the potential well. And then that means that you can end up with oscillations when you're then inverting in an incomplete basis. So just to give you a sense of what happens, so here, there are two curves over here. So to I-metric, you see that there's no difference between the magenta and the green curve in terms of the electron density. In the inset, you can see that these things vary, like, in a very small distance around the nucleus. But that causes these kind of spurious oscillations in the inverse problem.
Do you account for finite size effects of the core here, or?
Finite size effects of the core. So the densities are full ab-initio correlated densities, and
That's a perfect 1 over R potential.
Yes. So we when we're doing the inversion, because it's a non-periodic problem, yes, we can prescribe that at the quadrature points. You can prescribe it to be Z over R.
Yeah, I just mean that at the core you will deviate from that because the core is finite after all.
Yes, but these errors that you see actually are much far away from the finite size effects itself. Yeah. So we were able to get now clean solutions to this. The way we solve this is we use a PD constraint optimization. We use the systematically convergent finite element basis, which allows us to systematically improve the basis set accuracy. And for the incorrect asymptotics that are in the data itself, I'll tell you what we do with that. So in terms of PD constraint optimization, we are minimizing the L2 norm of the error in the density subject to the Kohn-Sham equations. As I mentioned, we are using this systematically convergent finite element basis. But now when it comes to the incorrect data itself, we have an error at the cusp. So what we do is we take a DFT functional, we compute the density with the DFT functional using the finite element basis, which can get the cusp, and we compute the density using the same DFT functional in the same Gaussian basis as that was done for the ab-initio correlated calculation. So now what we're seeing is the basis set error at a DFT functional, using a DFT functional, but if now this basis set error is independent of the choice of the functional that we are using, then we can go add this delta rho to the rho data, and that provides us better asymptotics, even using the Gaussian data. So that's how we fix this cusp condition. And we're also working with a collaborator who is now trying to generate this data using Slater basis, where you actually have the right asymptotics already put in. And in terms of the far field asymptotics, because this is a field formulation, and we enforce these constraints using adjoint functions, we apply homogeneous Dirichlet boundary conditions on the adjoint fields, and then prescribe the exchange correlation potential on the far field boundary. And here we use Fermi-Amaldi boundary conditions, which has the 1 over R decay. So here's how the exact exchange correlation potential looks like for hydrogen molecule at equilibrium and compared to an LDA calculation. And this is, as we start stretching the H2 molecule, this is how the exchange correlation potential looks along the bond length. One of the things that we always try to verify when we are doing this inversion is to see whether there's an agreement between the HOMO eigenvalue and the negative ionization potential, because by the Koopman's theorem, if you have the right exact exchange correlation potential, then this agreement has to be there. And we agree for many of the systems up to within a few millihartree. So this is the exact exchange correlation potential corresponding to a water molecule. And I'm just showing LDA just for the sake of reference. But there's some important qualitative and quantitative differences. Firstly, like you have this intershell structure over here, which is expected out of the exact potential, which the LDA completely misses. And qualitatively, you have a deeper exact exchange correlation potential compared to LDA. And this is where the hydrogen atom here is. At the hydrogen atom, you have like a slight local maximum that is the exact exchange correlation potential is predicting, whereas the LDA is actually predicting a local minimum there. So we are able to do these inverse calculations even for strongly correlated systems, such as orthobenzene. Now that we have all this data, we said, okay, can we go and let's say compare against other, how the other functionals are doing against this reference data. So we looked at hydrogen and stretched hydrogen. And you can see that there are fairly large errors even for this small system or simple system. I mean, stretched hydrogen is not simple. But one thing to notice is that if you look at the Minnesota functionals, they give very oscillatory potentials because Minnesota potentials or functionals have been only fitted to energies. They never took densities into account. The other functionals over here actually have taken densities into account, like which is why they perform reasonably well. And here is the error that I'm showing for the water molecule against B3LIP and SCAN0. Based on the systems that we have looked at, SCAN and SCAN0 seem to do the best in terms of qualitative and quantitative increment against the exact exchange correlation potential. And again, you can see that the intershell structure over here is predicted by SCAN and SCAN0, but not by other functionals. I think this is one of, I would say, the important slides, which is here for all these small molecular systems where we have the data for, we looked at these metrics of errors. So we're looking at the row-weighted error in the exchange correlation potential, normalized, L2 norm, as well as for the gradients of the exchange correlation potential, which are normalized. And we see that these errors are of the order of like 10 to the power minus 1 to order 1, which is saying that while these functionals have been like really good in allowing us to predict a lot of properties well, there is still scope for improvement. But on the flip side, if you look at the densities are reasonably accurate for all these functionals, which is of the order of 10 to the power minus 2 to 10 to the power minus 3, which, in my conclusion out of this data is that these functionals probably have to converge the densities another order of magnitude further, or they have to be accurate in terms of densities another order of magnitude further to actually really get us to better accuracies in DFT. And the other aspect is that the exchange correlation potentials are a much more sensitive quantity that if you actually use in your training and development of functionals, there's a potential to actually improve the functional description. So that is what we are trying at this present moment. We are trying to like see whether we can develop machine learned exchange correlation functionals at different levels. This could be at LDA, GGA, or you could have like even a meta GGA along with like some non-local descriptors over here. And the loss function that we're trying to optimize is on both the exchange correlation error in the energy as well as the potentials. And because we are including the potentials, the hope is that we'll get better functionals out of this. And so this is data that we've been collecting over the past few months. So here, the training for the LDA and GGA models has only been done on just few atoms and just a couple of molecules, hydrogen at equilibrium and lithium hydride. And we're not testing this against the whole, or rather, many molecules in the thermochemistry data set that are available. The reference energies over here are obtained using CI calculations. And I can tell you how these are obtained, for those who are interested. But if you look at it, if you compare NNLDA to PW92, the errors in the ground state energies are almost 300 millihartree per atom for this data set, whereas LDA and GGA is around 10 millihartree. And in fact, it's even better than the hybrids as well. So this is one measure in terms of ground state energies. I also have data for atomization energies, which I can share with colleagues who are interested. So these are early days, but it appears that using these potentials are providing a path for improving the functional description. And quickly, want to share some results. So this is a YBCD quasi-crystal. We are actually running it with this machine learned exchange correlation functional. There's no deterioration in terms of performance because the model implementation has been also well ported. So we get like very good efficiency, even up to 1920 nodes of summit for this 40,000 electron system. One interesting thing is that, okay, we are able to get the SCF iteration down to about 20 seconds. This is on summit, and this is the strong scaling study for the same system on Perlmutter and Frontier. And again, we're able to like get to about the 20 to 25 second in terms of the minimum wall time for these systems. We've also ported the inverse DFT code to GPUs as well. So we get almost a 20-fold speed up when we start using the GPUs. And in a given BFGS iteration, we are able to like get down to essentially about 20 seconds for this inverse DFT code. So we, in about 20 to 30 minutes, for a given molecular system, we can actually get the exact exchange correlation potential, and that's done once. That's about it. So now we are in a position to like rapidly generate this particular data. So with that, like, I'll conclude my talk. I've showed you that we can do systematically convergent large-scale cone-sham calculations. I've briefly presented some applications, like, where such large-scale calculations can be useful and what we're tackling. And then finally, just talked about what we're trying to do with the exchange correlation function approximation. Thank you for your attention.